Okay. Hey, gang. Since we are not meeting today, I decided that I would create a couple videos and upload some of the lecture stuff that we would have covered in class today. So I'm going to talk to you a little bit about the first half of Module 11. Trevor is standing behind the camera looking like a dork. So, okay, here we go. So this module is very different from some of the concepts we've been studying so far. And we are going to see and study concepts that cannot, actually we're going to not see them, but we're going to study things that we do not see in the physical world very easily, and that is sound and light. There are some similarities between sound and light, and namely they both travel in waves. So we need to start by understanding what is a wave. So a wave, as I've written up here on the board, is defined as a disturbance that propagates in a medium. So there are several terms in there you have to understand in order to understand what a wave is. Okay, so the first term that we're going to look at is disturbance. And basically, in terms of a wave, a disturbance is the thing that causes there to be motion and a propagation. Okay, so the disturbance is basically the origin of the wave, the thing that creates the wave. To propagate basically means to move something in a particular direction. And if you don't know what medium is, a medium is just a particular substance. Okay, so things can propagate through lots of different substances. They can move through air, through water, through other physical substances. Okay, so basically what we're talking about, a wave, a disturbance that propagates through a medium. We're talking about something that happens that creates a periodic motion that's going to move in a particular direction through some substance. And most of what we're talking about today, the substance that we're going to be talking about primarily in this chapter is the substance of air. Okay, so we're going to talk primarily about sound and light traveling through air. They can travel through other mediums, but we're going to primarily talk about traveling through air. Okay, so a couple things just to clear up. All right, first of all, the cause of the disturbance is not the wave itself. Okay, so we talk about a disturbance being something created that generates the motion, this periodic motion. That is not the wave itself. The disturbance causes the wave to happen. Okay. Also, not every disturbance is going to constitute a wave. So, for example, if you stand in the water and you wiggle your big toe, right? You're making a disturbance, but you are not creating necessarily a wave. Okay. We also have to, in your head, you have to kind of, obviously, if you've studied trig and all that, you've looked at sine and cosine waves, and some of that may be making more sense to you. But understand that when we're talking about a wave, you have to differentiate that from what we think of as waves, right? We think of waves rolling in multiple sets, right? But understand that when you're talking about a periodic motion and this kind of a wave that's moving, you're talking about there being one disturbance and motion that continues to move forward, okay? So in a water sense, you might, if you drop say you drop a stone into a pond and it makes ripples, you might think of all those ripples as wave, right? Waves, plural. But really, that one disturbance, the pebble being dropped, would create a wave that would ripple outward. So all of those ripples would really constitute one wave caused by the disturbance of the pebble, and then that would be propagating through the medium of water. So hopefully that kind of helps understand what waves are a little bit. So let's also look at the physicality of a wave in terms of mathematically. Okay, so a wave looks like this. It's some kind of periodic motion, okay? It's got several components to it, all right? It's got these, this distance above equilibrium. This line we've got here is our equilibrium. Okay, so we've got the wave traveling above equilibrium and below equilibrium. The distance it travels above equilibrium, those are the crests of the wave. The distance it travels below equilibrium is the trough. Okay, now, this may not be drawn perfectly, but in a wave, the distance between the equilibrium and the crest will equal the distance between equilibrium and the trough. And that distance is what we call our amplitude, which is noted by this green here, okay? So our distance above and below equilibrium is our amplitude. And when we measure from either crest to crest or trough to trough, we get the feature that is the physical feature that is known as the wavelength. Okay? And again, measuring from crest to crest or trough to trough, you'll have the same measurement in a true wave. All right? So, we're going to talk about how we mathematically represent frequency. Okay? So, frequency in a wave is f, and that is defined as the velocity over the wavelength. Okay? So we've got velocity, and really when we say velocity, what we're meaning is speed. We're not incorporating direction into this particular equation. And then, real quick, I'm going to look at the units here. So frequency, right? Velocity over wavelength. Velocity is meters per second, and we divide that by frequency, which is going to be in meters, right? Which is the same as taking my meters per second and multiplying it by 1 over meters. My meters cancel out. I get a unit of 1 over seconds, which we know from previous units is the hertz. So that makes sense mathematically. So obviously, we also know that frequency and wavelength are inversely proportional, meaning as one gets larger, the other one gets smaller. So if we have a large wavelength, we're going to have a small frequency. And if we have a small frequency, we're going to have a large wavelength. Okay? So remember, or I haven't mentioned it yet, frequency is basically the number of times a wave is going to travel through its cycle in a given period of time. Typically, we measure waves in frequency in seconds, but it could be some other time unit as well. So, right, so it's the number of times it moves through its cyclical motion in a certain period of time. Okay? I'm going to say that I didn't particularly like the author's definition of frequency. He says it's how many waves hit a certain point every second. And I've just emphasized the fact that this is one wave. So really, he's not saying how many waves. He's saying how many cycles of one wave hit a certain point in a second. Does that make sense? So again, I'm talking about one wave, the frequency being how quickly that wave occurs. So obviously, if you have a small wavelength, then it's going to cycle through much more quickly. If you have a much longer wavelength, it's going to cycle through much more slowly. So, all right, the next thing I'm going to talk about, I'm going to stop this video and start another one. The next one's going to talk about the transverse wave, and the longitudinal wave, but I'm going to erase the board and redraw some things. So, back in a minute.